Hello, this is module M4.7 covering interference and diffraction. We've seen interference before in Unit 1 when we talked about general wave interference, and we talked about interference with sound waves. In this module, we will look at how light waves interfere with each other. If you're a little bit rusty on interference, in particular totally constructive and totally destructive interference, I suggest you go back to your Unit 1 notes and review those topics. In Unit 1, we talked about two different types of waves, longitudinal waves and transverse waves. Electromagnetic waves, including light, are always transverse waves. Another way to classify waves is by how they propagate. In particular, electromagnetic waves can propagate either as plane waves or circular waves. So far, we have mostly represented light as plane waves. Plane waves travel in a single direction so that each wave crest is a straight line moving in that same direction. A single peak or trough moving in the same direction across its entire length is called a wavefront. A plane wave can be represented symbolically by a series of parallel rays. In water, a series of waves moving in a line towards a beach is a pretty good approximation of a plane wave. Circular waves, also called spherical waves, are generated at a point source. A familiar example of a circular wave in water is the ripple effect, in which a disturbance creates a wave that radiates outward from the central point of disturbance. The wavefront of a circular wave is a single peak or trough expanding radially outwards. Circular waves can be represented symbolically by a number of individual rays radiating outwards from a source. In the resources section, there is a link to a video on waves. The first minute has a very nice animation showing a circular wave from the top and from the side. If you want to, you can watch the whole video for a quick review on some wave basics. Both plane waves and circular waves can experience interference when two waves intersect, or when two wavefronts cross each other. In the resources section, the picture shown here is animated, so that you can follow a single peak or trough, the red and blue lines, as the two wavefronts hit each other and interfere. In the middle portion, where the two waves are interfering with each other, the brighter blue and brighter red lines indicates an area of total constructive interference, where the amplitudes of the two crossing waves combine, giving higher peaks and lower troughs. The black lines that you can see cutting across the area where the two waves are interfering with each other are areas where the two waves combine destructively. Because these are lines of destructive interference, they don't represent peaks or troughs. Instead, the black lines represent areas where the combined amplitude of the two waves is equal to 0. This picture shows two circular waves, each emitted by a point source, interfering with each other. In the resources section, this picture is also animated. Here, the blue represents peaks and the black represents troughs. Notice the lines that appear to be a darker or blurred blue that appear to radiate outward from a point exactly between the two sources. These lines represent areas of total destructive interference. Again, neither a peak nor a trough, but where the combined amplitude of the two waves equals 0. In addition to the animation in the resources section, there is also a link to the PhET simulation that allows you to experiment with interfering circular waves. Click on the second option in the activity menu labeled Interference. In the Interference activity box, at the bottom right of the toolbox, you can select water waves, sound waves, or light waves. In M4.2, we talked about 3 different types of light. So far, the interference patterns we have shown have assumed that the light rays were monochromatic and coherent. That is, all waves had the same wavelength and are in phase. You can probably imagine how complicated interference patterns would be if we tried calculating them for white light with many wavelengths in all different phases. So unless otherwise stated, we are going to stick to monochromatic, coherent light, just like the light used for laser pointers. What happens if we have many point sources in a line, each emitting a circular wave? Well, each circular wave will interfere with its neighbors. So long as all sources are emitting circular waves that are in phase, all of the combined interference will result in an approximate plane wave moving perpendicularly away from the line of point sources and rounding off around the sides. In fact, if the line of point sources is long enough, the wave acts exactly like a plane wave, except for at the very far edges. In fact, Huygens' principle asserts that this idea of many point sources combining to create a linear wavefront is exactly how all plane waves behave. Huygens' principle goes even further, asserting that every single point on a wavefront acts like a new source of wavelets that in turn spread out in the forward direction, forming the next wavefront, and then the next, and then the next, and so on, creating the plane wave that propagates in the forward direction. Huygens' principle can also explain the behavior of a spherical wave in the same way. In fact, Huygens' principle helped physicists make sense of some of the most mysterious properties of light. So far, we've been talking about light rays that travel in a straight line. And yet, if you have ever looked at light coming through a window or a door into a very dark room, it certainly seems like the light is bending around the opening just a little bit. Is this another way to bend light, to add to reflection and refraction? And if so, what makes it happen? Huygens' principle explains how this is possible. When a wave hits a barrier that allows only a small opening, lateral interference causes areas of destructive interference immediately to the sides, but the wave directly in front of the opening approximates either a plane wave or a spherical wave, depending on the size of the opening compared to the wavelength of the wave. Directly in front of each point source along the length of the slit, the wavelets experience totally constructive interference, creating a plane wave moving in the same direction as the original wave before it hit the slit. The next series of point sources is slightly wider. This continues, creating a plane wave that gets slightly wider as it propagates. To the sides of this plane wave, the waves from each point source start to interfere destructively, so that the wavefront fades out to the sides. The net result is that light rays appear to bend and spread out slightly around corners or openings. This effect is called diffraction. For openings that are much larger than the wavelength, the wavefront passing through the opening will approximate a plane wave because, according to Huygens' principle, there's a long line of point sources between the two edges of the opening. The amount of bending along the sides will be small compared to the width of the opening, and light at the human scale has plenty of opportunities to be absorbed, reflected, or refracted by other objects, or even just by the air in the room before reaching our eyes. This is why, at the human scale, diffraction can only be observed in certain circumstances. Sound, on the other hand, which has wavelengths roughly the same size as human doors and windows and walls, is able to bend completely around human-scale obstacles. This is why you can hear people around corners, but you can't see them. Diffraction in light is therefore most noticeable when the size of the opening is comparable to the size of the wavelength of light, the nanometer scale. Let's take a closer look at how light bends when it passes through an opening or slit that is about the same size of its wavelength. If light from a monochromatic, coherent source shines on a small slit that is the same scale as the wavelength of light, one ray from each point source within the slit will travel straight to the screen. The peak from each of these rays will hit the screen at the same time, and the troughs of each of these waves will hit the screen at the same time. However, each of these point sources doesn't just emit the one ray that heads straight to the screen. They each also emit light rays at every angle, radiating outwards. For example, there will also be a set of parallel rays from each point source that looks like this, for every angle measured from the center line of the wavefront. So the light that actually reaches the screen at a given point, marked here with an X, will come from a set of rays that looks more like this. Let's consider the interference for just two of those point sources, the one at the very top and the one at the very center of the slit. The light from point 1 travels a distance d from the source to the point X on the screen. But the light from point 2 has to travel a little bit further to get to the same point X on the screen. Since the rays start out in phase from our monochromatic coherent light source, if the path length difference is equal to one wavelength, the two rays will arrive at point X in phase. This means that there will be constructive interference between the two sources at point X, and point X will receive the maximum possible intensity of light from those two rays. However, if the path length difference is equal to 1/2 of a wavelength, the two rays will arrive at point X completely out of phase, resulting in totally destructive interference. The screen will not receive any light from these two sources at point X. If the path length is somewhere between 1/2 wavelength and one full wavelength, this will result in partially constructive or partially destructive interference, and the screen will receive some light, but not the maximum intensity. This means that to find points on the screen that do not receive any light from the two sources, we need to figure out the angle between the two rays that will give a path length difference of 1/2 of the wavelength. But how do we find this angle? To find the angle theta, we must resort to a little bit of geometry and trigonometry. If we draw a line perpendicular to L2 that goes back to the top of the slit, the angle formed by this line is equal to the angle formed by the two rays. This line will intersect L2 so that the small bit of L2 to the left is equal to the path length difference between L1 and L2. Using the rule that sine of theta is opposite over hypotenuse, we can now determine that the path length difference between L1 and L2 is just the width of the slit divided by 2 times the sine of theta. What about all the other point sources of light between the two ends of the slit? Well, it turns out that although the geometry is a little bit more complicated, as long as the distance between any 2 points is W/2, they will all have the same path length difference to a given point on the screen. So each point from the top of the slit to the center of the slit can be paired with a point from the center of the slit to the bottom of the slit, so that each pair of points has the same path length difference. This same relationship is true for any point on the screen. So now all that is left to do is to find the particular angle theta made between the center line of the wavefront and the wave coming from the point source at the center of the slit that will give a path length difference of delta L equals lambda/2. The point that a ray from the center of the slit with this angle hits the screen is the point where all rays will destructively interfere with their corresponding partner. So this point on the screen will not receive any light. It will appear as a dark line or a dark fringe across the screen. Notice how the 1/2 cancels on each side of the equation, giving W sine theta equals lambda. Notice that this same angle theta could just as well be measured from the center line going in the other direction. So there will be another dark fringe on the other side of the screen corresponding to the same angle theta. We could play this entire game again, this time using W/4 instead of W/2. Now, each point source partners up with a point source a distance W/4 away, so that all the point source pairs have the same path length difference as all the other pairs. This gives us a second angle, this time with the equation W/4 sine theta 2 equals delta L. We can therefore find a second angle and a second location on the screen that will not receive any light due to the total destructive interference cancellation between each pair of points. This creates another pair of dark fringes on the screen, one for theta 2 measured above the center line and another for theta 2 measured below the center line. We can keep doing this indefinitely, using the width of the slit divided by successive even integers, until the angle exceeds the maximum angle at which light will diffract, or until the point on the screen is so far away that light will no longer have measurable intensity, or until we just run out of screen. We can package this all up into a single equation by writing this as W/2m, where m is an integer, times sine theta equals lambda/2. Simplifying, we get W sine theta equals m lambda. Note that for theta equals 0, which is the point on the screen directly opposite the center of the slit, the equation does not work because the sine of 0 always equals 0. We can't find the angle where destructive interference occurs if the angle is known to be 0. So there is never totally destructive interference at the center of the screen. Instead, we notice that delta L is always 0, meaning that there is always no phase difference between each of the paired rays. Thus, the point on the screen opposite the center of the slit always has maximum constructive interference, meaning it is always the brightest spot on the screen. The light that reaches the screen will appear across the screen as alternating light and dark spots. In the end, if you plot the intensity of light striking the screen, you clearly see a very bright spot in the center and then alternating light and dark spots until the entire diffraction pattern fades. We can determine exactly where these dark fringes appear on the screen with just a little bit more geometry. Once we know theta, we can determine the distance from the center point on the screen to the dark fringe using tangent theta equals S over D. Sometimes we can make this even easier. If theta is very small, then the sine of theta is approximately equal to just theta in radians. In degrees, 10 degrees or less is considered small enough to go ahead and make this approximation. Theta will be a small angle when d is much greater than the width of the slit. So we can say that when the distance d between the slit and the screen is much greater than the width of the slit itself, theta equals m lambda over w. Similarly, if theta is very small, the tangent of theta is approximately equal to just theta in radians. This means we can combine these two equations, arriving at s times w over d equals m lambda, where m is any non-zero integer. In summary, light is a transverse wave. Two basic types of wave are plane waves and circular or spherical waves. Huygens' principle states that every point on a wavefront is a source of wavelets that spreads out in the forward direction at the same speed as the wave itself. The new wavefront is a line tangent to all the wavelets. Huygens' principle explains many strange behaviors of light, including diffraction, the bending of light around corners or openings. The effect of diffraction is most noticeable when the wavelength of the wave is about the same scale as the opening. When light diffracts through a small slit, an opening on the nanometer scale, it will create an interference pattern on a screen that is placed in front of the slit. This pattern appears as a large central bright spot surrounded by alternating bright and dark fringes. The key equations to find the locations of dark fringes on a screen are the width times the sine of theta equals m times the wavelength, where m is a non-zero integer. Tangent of theta equals s over d, where s is the distance from the center of the screen to the dark fringe, and d is the distance from the slit to the screen. If the distance from the slit to the screen is much, much, much greater than the width of the slit, then you can simplify this to m lambda equals sw over d.